Okay, I'm good now. Thank you. Okay, so U cross V, if you can't use the 3 by 3 determinant method because they didn't give you the component form, and you don't know the components, then you're going to use the information they gave you for this example. Check this out right here. This is going to be your key to life for this particular problem. Oh, well, that was nice. That's what PDF Annotate does for me. So you've got the fact that the magnitude of the cross product, which they're asking for in this example, we don't even need to get the cross product. We can immediately get the magnitude by performing this formula because they gave me all the ingredients for this formula. Cool. So we're going to do just that. I'll write it down again. So here's the little theorem that tells us, hey, I'll put the sine theta in the front just because I think it looks prettier. So we're almost done. We're just going to substitute 120 degrees for theta, and then the magnitude of u is 25, and the magnitude of v is 30. And then, ooh, crap, you might want to look at the trig unit circle I gave you on that first lecture and go, what is sine of 120 degrees? Ah! I think it's square root of 3/2. And then when you whip out a calculator and multiply all these together, the exact answer is 375 times square root of 3. Please do not give me the decimal answer. That's not exact. That's actually the approximate answer. This is the exact answer. So if they do ask you for approximate, and sometimes MyMathLab does, that means they do want you to whip out a calculator, type it in, and give the decimal result. Okay? Now, you're going to have to use your right hand here and perform the right hand rule on part B. How are you going to answer this question? Is V cross U, that vector, it's going to be either sticking straight out of the page, so here's V and U over here, here's your diagram. Is V cross U going to come out at you, or is it going to be punching into your page? Anybody know?
It's inside.
Yes, it's gonna go into the page. And the reason why is if you start curving your fingers, and you're gonna have to sort of turn your wrist sideways, when you start curving your fingers through V first, because it says V first, and then you curve it through there, once you curve everything, your thumb is gonna be sticking downward. So there's your thumb, and there's your fingers, and then your arm is gonna be kind of weird like that. That's a terrible picture, but whatever. Okay. How about letter C? True. Oh, by the way, I put a problem like letter B on a quiz in MyMathLab. You better know how to do it. Right hand rule is important. True or false is the vector u, any vector u, just a 3D vector, when you take the dot product of u with this vector, u crossed with some other vector v, will you get 0? You guys know this is a fact that you want to be mindful of. When you get a dot product of two vectors equaling 0, the two vectors are orthogonal. Remember this? Does anybody remember this handy fact from this past week's worth of lecture? Please say yes, people, because if you don't, time to check out now, okay? Get out while the getting's good. This is a key fact you're going to need for the entire semester. Please don't lose sight of it. So they're basically asking, true or false, is u, this vector u, and the cross product u cross v, are they going to be orthogonal with each other? Yes or no?
Yes.
The answer is yes. Why?
Well, because the answer is going to be equal to 0.
But why? Why is u and the vector u cross v, are those guys really orthogonal to each other?
No. On your theorem of algebraic properties of the cross product on number 6, when you have a vector times the cross product of two vectors, you can.
Yeah, but this, hang on a minute, Rosie. This involves three completely different vectors, u, v, and w. In this true-false problem, I don't have a u and a v and a w going on in that conversation. I simply have a u and a v. So I get that number 6 kind of has the look like you're taking a dot product and there's also a cross product involved, but it's not even coming into the situation for this true-false. Okay, you got to be careful here.
With that same page on number 4, if you scroll down, so vector u is being multiplied by, no, sorry, scroll back up again. Right there. Vector u is being multiplied by vector 0.
There's no 0 vector going on here,
wait.
though.
Oh,
Professor, when we took the cross product and we said that
wait.
the vector pointed into the page,
Yeah.
was it perpendicular to
Yes.
vector u?
Yes, period. Yes, you guys still aren't getting the cross product. I must have done a really crappy job with this lecture, and I apologize. You guys aren't getting it. It's really unfortunate. I'm going to try again. Let's see if I could do a better job. Look at this picture right here, Focaroonies. Have a cup of coffee and look at this picture, okay? Whoops. Oh, geez Louise. Okay. What do you notice about this diagram here? You got u down here and you got v down here. Just 2 vectors, not 3. We're not dealing with u, v's, and w's. You got a u, you got a v. You use your right hand rule, and then you get your thumb pointing in the direction of u cross v. From this picture, and it's my PDF annotated is just crap, sorry. From this picture, can you see that u cross v is indeed making a 90-degree angle, so it's orthogonal with u? Please say yes.
Yes.
Yeah.
Thank you. Thank you. By definition, people, by definition, u cross v from this picture, please burn this picture or tattoo it on your butt cheeks or something, I don't know. That is saying, because of the nature of it, u cross v, by definition, is going to be orthogonal to its 2 original vectors that helped create him. So the answer here is true. By definition. Okay, now let's do some stuff that I like to put on quizzes and exams. Hint, hint. Oh yeah, it's coming. Quiz 2, baby. I'm going to put something on here like this. Almost exactly like it. And if you can't operate in picture in 3D what's going on, notice I got I, J, and K. Who are I, J, and K?
Unit vectors of x, y, z.
Yeah, they're unit vectors that point in the positive x-axis, y-axis, and z-axis direction, respectively. So I hat, that'd be the I that you see all over here, he is pointing, he's 1 unit long, so he's like that. So, you know, his tip is right there at the point 100 there. And that is a crappy orange color there, sorry. So there's I hat. And then J hat, his little tip is located at 010 right there on the y-axis, and he's 1 unit long. And then you got the K hat here, and his tip is located at 001. So the component form, you know, the component forms would look like this, just so you know, although that's not what they're asking us for. What are they asking us for? So using your right hand, if you took the cross product of I and J, would you get the standard unit vector K? Yes or no? So if you can imagine your fingers curling through I first and then curling through J, and then you make a fist and then see which direction your thumb is pointing to, it's going to be pointing in the positive z-axis direction. So true. That is a true statement. Now, if you still don't get the right-hand rule, you could do this problem the hard way. So what do I mean the hard way, where you're wasting valuable time? If you want to, I'm going to give you 3 hours on this week's quiz too. I guess you might have some valuable time to waste. But if you're like, well, I still don't get this stupid right-hand rule, I'm going to do it the 3x3 determinant way. Okay, fine. Set up the I hat, j hat, k hat across the top. The components for I hat look like that. The components for j hat, and then do this. Remember this from last time? And I claim you are going to get 0, 0, 1. So you will get, by definition, the k hat unit standard vector there. It'll work out. And if you want to do it this slow way, go for it. But because I already know that I can easily cross the product of I and j, just because, you know, they're the positive x-axis and the y-axis direction, it's kind of easy peasy. Okay, now check out number 2. What about I cross product with k? So if you have your fingers curving through here and then here, I claim that when you close your fist like this, your thumb is going to be pointing in the negative y direction. So this is false because it should be negative j hat. And if you don't believe me, you certainly could do this letter B the slow way. You're like, oh, okay, I don't buy it. All right, so you know, do I hat k cross k hat using the 3x3 determinant method. Sure, go knock yourself out. And I claim you're going to get a 0 I hat minus 1 times j hat plus 0 k hat, which is the vector 0, negative 1, 0, but that is equal to negative j hat, okay? And lastly, what about negative j cross product with k? Is that equal to negative I? So if you looked at your little diagram here and you're trying to figure out, negative j hat is this vector pointing that direction, kind of the back side of your y-axis. So if you go a negative j hat cross with k hat, woo! That's really fun. You will get negative I hat. So this is going to be true. If you want to do it the slow way, go right ahead. Okay, questions?
Number 2, how would you have positioned your right hand? Like, say you're starting from I.
So you're going to have to, and this is sort of like me standing over here. This is hard. You're going to have to sort of crank your fingers. They're going to have to start. Can you tell those are my fingers? They first fluff through the I hat, and then they swing around to go through the j hat. So I'm curling my fingers over here. And then when I finally close my fist, but don't make a fist because you want your thumb to be pointing somewhere. Excuse me, I'm doing I. Oh, you wanted number 2? Sorry, I'm doing this wrong.
Number 2.
Number 2. Okay, number 2 is I cross k. So you're going to have to get down. Here's I, here's k. You're going to have to go sort of like, it's going to be where you have to like go underneath here, where your fingers start curving through the I hat, and then they curve through the k hat. Now, folks, if I were in person, it'd be easier. So if you could look at me, let me do something like this. Okay, can you see me?
Yeah.
You're going to have to like get underneath it. And I mean, it's kind of hard. Like you're going to have to get underneath it and go, okay, I'm going to go like, and this is why I was telling you that story of all these physics people in the room doing all this crazy stuff, like contorting their body. Like, okay, I'm going to get underneath it and have I hat and then K hat and then like that. You know what I mean? And then it'll be pointing in the negative J direction. So you have to like contort your body so that your fingers always curve through the guy who's first, and then when you're cross-prodding the second guy, and then keeping your thumb out in whatever direction. You may have to, you know, move your hand around so it's like, so you know, see how my hand's like this way? Like I'm really contorted here, like holy crap. Like so. So it's a little bit tricky. And like I said, if I were face-to-face, it'd be easier for me to show you the exact you know, contortions that my body is making, like my whole underside here. Like I'm trying to get underneath it so that I could curve my fingers first through the one, then for the other, and see which way my thumb's pointing. Boom, or boom, it's coming at me. Or boom, it's coming straight at you. you know? So that's how you roll. I don't know if that helps any. And if it doesn't, I apologize, but we're gonna move on. Go watch a video about it. So I like to have memes. So there's my meme for that one. Don't do the right hand rule with your left hand. Okay, people, it's not gonna work. If you're not laughing and you're not having fun right now, you're not doing Calculus 3 right. Because you should be having a good old time in this class. This stuff is awesome. This is fun material. I mean, would you rather be doing sequences and series?
Probably not.
Probably not. Okay, so, you know, you got to look at the upside, people. Yeah, no more of those, right, Nick? Like, please, God, no. No more sequences and series. Okay, let's talk about the triple scalar product. Now, your book, did I mention that Briggs sucks? Not today. Briggs sucks, and he doesn't go over the things I'm about to go over with you and as well, like any detail at all, and yet there's some homeworks on it in his book. Oh, thanks, Briggs, for like assuming we know it already. What? So I'm going to give you everything. So there's this idea, the triple scalar product, which is also called the box product, and it looks like that number 6 on that theorem. And it turns out there's 2 ways to get this. You could first do this, you know, you guys all know how to do a cross product of 2 vectors, you know, go do the 3 by 3 determinant method, and then do the dot product. Okay, that's one way to do it. But wouldn't you like a quickie shortcut? I'm going to show you the quickie shortcut. You use the 3 by 3 determinant method on steroids, where you put U1, U2, U3 components along the top, not IJK, and then V goes in second row and W's components in the third row. And then you expand, well, all you linear people, you know this is a regular 3 by 3 determinant. So you could expand along any row or any column, provided you honor the matrix of cofactors. So I don't want to get into all the different ways to do that because that's more of a linear algebra professor's purview. So we'll just expand along the top row because you already know kind of how to do this. You're going to have a 2 by 2 times U1 minus a 2 by 2 determinant times U2 plus a 2 by 2 determinant times U3. And then to find what goes there for these 2 by 2 determinants, you know, you block out the row and column that U1 lives in and you get these numbers. And then you take that 2 by 2 determinant, and then here you block out the row and column that U2 lives in, so you get V1, V3, W1, W3, and find another 2 by 2 determinant. It's going to be just a pure number, plus a 2 by 2 determinant times U3. And this is just going to be a pure number. It's going to be a pure number. Okay, so what? What does the number have to do with the price of eggs, geometrically speaking? If you take the absolute value of that number, just to ensure it is a positive result, it actually corresponds to the volume of a solid, which is awesome. And this is a picture of the solid. What do you mean? And they call it a parallelepiped. I'm not sure if I'm even pronouncing that right. And so the volume of that parallelepiped is the absolute value of that box product. Cool. Now, how did they get that? So the idea, like, why is this true? Like, why? So if you didn't know anything about, you know, that this was actually true, here's the idea. The base of this solid is down here. So the volume is going to be equal to the area of the base times the height of this solid, this parallelepiped, okay? So the area of the base, actually, you guys already know. Why? So we want to find the area down here. Because you have, it's basically the base is a parallelogram. And you have 2 vectors who are forming adjacent side lengths of that parallelogram. So I claim that I hate my Microsoft Surface Pro. And the area of that base is the magnitude of the cross product of V and W. And we learned that last time when we were talking about areas of parallelograms with the cross product. Times, now what's the height? Well, the height is actually this right here. If you draw a imaginary horizontal line here, how tall this solid is that right there. And it's not the length of U, okay? It's not. So, well, how do you get it? How do you get this height here, which would be the distance from here to the origin? Well, the claim is that you're going to have to project u onto the the cross product, if you will, of v cross w. So let's go like here. If you use the right hand rule, so there's your right hand, your v cross w is perpendicular to both u or to both v and w. So you want to project the u vector. So here's the height, people. It's the projection, the magnitude, I should say. So I'll use magnitude. Projection of u onto v cross w, and then take the magnitude of that projection. So from last time, Monday's lecture, which is, projections are going to be on quiz 2 this Sunday, know how to do it. How do you project u onto v cross w? And then we'll take its magnitude. How the heck do you do that? So I'll append a page, and this is worth doing in slow motion because it's kind of a review of last time to see if you remember any of this stuff. And yeah, I know it's there's a lot of letters and stuff swinging around here, and maybe that's losing you. And I don't know what to say other than Calc 3 can be somewhat conceptual and somewhat theoretical compared to Calc 2. Calc 2, my old mentor, Dr. Arnold Vallone, who he passed away 7 years ago, but he was a math professor at San Diego State, but he also was a former engineer, similar to me. So I bonded with him right away because we were both former engineers, electrical engineers who became math professors. And I remember, this is about a year before he died, and we were chatting. He's like, yeah, I hate teaching calculus 2. I hate it. I'd rather teach calculus 1 or calculus 3. And I'm like, whoa, where is that coming from? He's like, oh, it's just so many formulas and all that integration techniques. And it's just, I hate teaching it. And I went, got it. So just to let you know, calculus 3 is more fun. Lots of vectors.
Miles.
What's that?
It speaks miles about a person when they hate calculus 2 that much.
Yeah, he just went on and on. I just died laughing. I don't mind teaching calculus 2. Now, there are some parts that get a little bit sticky because students tend to really start, giving me lots and lots of tears when they're doing the series. I get it. It's sad. It's a challenge. Let's put it that way. Okay. So what are we doing here? So this is going to be a big old magnitude of, and remember, projection is a scalar times a vector. And the vector is the v cross w vector here. So when you project u onto v cross w, this scalar, remember, was a fraction. You're going to take the dot product of u with the cross product v cross w. Okay, fine. And then you're going to take the magnitude of v cross w and square it. Now this whole thing, we're looking for a magnitude because we want volume. Volume's got to be a scalar. So then what? So then we use this knowledge of what happens when you take a magnitude of a bunch of crap. Well, this right here, this numerator is just a pure number. And when you put a magnitude over it, you're just saying force it to be a positive result. So whatever that dot product is, we want the positive result if it just happens to be negative. When you take a magnitude of a magnitude, nothing changes. So this denominator is still going to be a magnitude squared. And then times, and then we want the magnitude of that vector there, the v cross w. And now what are we going to do? Oh, I forgot something here. That's the height. We want to get the volume, so we forgot the area of the base. So if I'm going to do, this right here is the height. So if I'm going to really try to figure out, as we're going here, after I reduce this to lowest terms, come on, computer, please stop messing with me here. So one of these magnitudes cancels. So what are we saying? This right here, people, is the height. Absolute value over this. So this right here is the height of our parallelepiped. So if I go back to my little diagram of my solid here, that is the length of how tall it is. So another way to figure out height is to drop a perpendicular down from that vertex down to the ground. So now the actual volume, remember, is base times height. So volume is base times height of this parallelepiped. And remember, the base was a parallelogram, so the area of the parallelogram was the magnitude of a cross product. So if you multiply base times height now, like this, I hope you can see that you can reduce this to lowest terms, right? Boom, boom, and then what's left? And this is the box product forced to be a positive result just because you want it to represent something in the real world. So I'm done with that example. Pretty cool? That's just a little derivation for you. So I'm not going to ask you to derive this in a quiz or on an exam. Well, so what do you want us to do with it? Okay, I'll tell you. I will, most likely on your homeworks, you're going to see somebody's going to give you a U, a V, and a W that will be adjacent edges. You see those are adjacent edges of a parallelepiped, and they're going to go, hey, those vectors are adjacent edges. Go get me the volume of that guy. And you're going to go, oh, I'm going to use the 3x3 determinant method. And then if I get a negative number by chance, I'll just put absolute value bars around it to ensure it's positive, since it's going to be representing a volume for me. Okay, easy peasy. Don't make it harder than it is. Like, don't overthink it. All right, let's take a look at wrapping this up. How about you and a buddy find the volume of this parallelepiped? I'm going to put you in breakout rooms. You and a buddy are going to go do this. Wake up, people. Look alive. All right, let's see. We've got 29 people in the room. I'll make 9 breakout rooms. Well, if I can enter in a number bigger than 1, that would be nice. Ah. Okay, once you're asked to join your breakout room, please do so, okay? Bye, have a good time. Hang on. Danielle, Emily, are you guys there? Danielle, can you hear me? Emily, can you hear me? You can talk to me in the chat box. Okay, can you guys see my screen at all?
Yeah.
Okay. So what did you guys get? Shout it out.
I
Put it in the chat box
I
too.
didn't even get the answer.
Didn't get the answer. Okay. Not enough time?
Not enough
We
time.
got 24.
Okay.
I got 36 units cubed.
Right. Augustine got it 36 is correct. Veronica and Kiana got 36. Okay, fantastic. 12. Well, something may have happened there with some arithmetic. We'll find out. Not enough coffee? I'm with you. There's never enough coffee. You can always have more. Yesterday, I had 2 cups in the morning. I had a monster drink at 1, and then I went and had a double cappuccino at Starbucks. I'm numb to it now. It's like doesn't even kick in. All right,
That's
so
a
let's
far
find
step
out.
away from your
What's
Lipton.
that?
That's a far step away from your green tea in the morning. Oh my God.
I don't drink as much green tea anymore. This doesn't do much for me. I did have one the other day, though, I must say. Okay, folks, so why is 36 the answer? All right, let's take a look here. So I claim that we're going to first get the 3 by 3 determinant, which may be a negative number. And then since this is what we want it to represent a volume, we're going to have to take the absolute value if we do get a negative number, which is possible. So what I'm saying is volume is going to be the absolute value of this triple scalar product.
Professor,
Okay? Yes.
will you also be recording this part?
Yeah, well, I believe we're back to being recorded, Yara. We're
Oh,
still
okay, sorry.
now recorded, so you're fine.
Okay.
Don't worry. So what you're going to do here is we're gonna first get what's inside the absolute value, which may be, it could be actually 0 also. That's also a possibility with dot products, as you know. So I'm going to set up this matrix, and you haven't taken linear algebra yet. It's like a matrix. So I'm going to put U's components up top, and in the second row, I'll put V's components, 0, 2, negative 2. And then the last row, I'll put the W components. Okay, yes, I know I'm going fast. When I went in the breakout rooms, everybody's going, oh, you're going too fast. And I'm like, it's not going to change. I might even go faster as the semester goes on. I'm sorry to say this, but if you need to watch the recording once, twice, 3 times, rewind it, whatever it takes for yourself. This class goes very quickly, and that's how we roll, okay? So I'm going to have a 2 by 2 matrix determinant times the 3, because I'm expanding along the top row. Instead of an I hat there, it's a 3. Minus, anytime you do these 3 by 3 determinants and you're expanding along row 1, the second term is going to be a minus. A 2 by 2 determinant, if you blocked out the negative 5, he's going to go right here. The 2 by 2 determinant would be 0, negative 2, 3, 1, plus a 2 by 2 determinant times the last guy in that top row, which is a 1. And then blocking out the row and column that the 1 lives in, I'll have these numbers, okay? Oops, I forgot to do these numbers here. Okay, now what? So you're going to use your knowledge of a 2 by 2 determinant. So you multiply the 2 numbers along a major diagonal, 2, and you subtract minus the product along the minor diagonal. So 2 minus a minus 2, and that's going to multiply by 3. We'll do the arithmetic in a moment. Minus, now you're going to do the product of the major diagonal values, but 0 times anything is 0, minus the product along the minor diagonal. 3 times negative 2 is negative 6, and that's going to multiply with the negative 5. Plus, and now you're going to have a number times 1 here, 0 minus 2 times 3 is 6. Okay, what the heck here? This looks like it's going to be 4 times 3. This right here is a positive 6, so, but you have a minus here. So you've got like minus 6 times a negative 5. So that's negative 30. So you're going minus a negative 30, which of course will be plus 30, plus, and this right here is negative 6. So this looks like it's going to be 12 plus 30 plus a negative 6, and that is going to give me what? 42 minus 6, which is 36, and then units cubed. Okay? And luckily it wasn't a negative number. It was already positive, so we're safe. So the volume of the parallelepiped that has all 3 of these vectors as adjacent edges, and if you want the picture of it, it's on the previous page, in your course reader, you go back, this is what the heck a parallelepiped looks like. Looks like a box that somebody kind of tried to push over a little bit, like it's slanted over a little bit. And it's got the UV and W vectors as edges. Okay, that's all it is. And we got the volume.
Professor, I had a conceptual question about that.
Sure.
So is the base usually going to be determined, or do we have to figure that out?
The base is going to be given to you because two of the vectors, which are serving as edges, are
Yeah.
automatically there for you, Aloe.
Okay.
So can we choose any two of the vectors to act as our edges?
Yes.
That's what I'm getting at.
Yeah, it doesn't really matter. Like if you wanted, if I looked at this thing sideways and I wanted this right here to be the base and then the height to be, if I drop a perpendicular down that way, you certainly can, have your box product be all discombobulated. So what does that mean? Would I get a different number? What do you think?
Probably not.
No, you would not. You would get the same number. Now, when you do the 3x3 determinant, let's say like I did, you would have the guys just in a different order. You might have the V, then the W, and then the U be the bottom row, okay? But any way you slice it, you're still going to get a value. Now, I want to warn you, when you do it where you're moving around the rows, this value 36 might get negativized. So you may get, when you start moving things around, and if you take a linear class, you're going to learn why. I'm not going to get into it here. Good luck. You may get a negative 36, but you have to remember that the theorem says if you are using your triple scalar product to represent the volume of the parallelepiped, you take the absolute value.
Okay.
Does that answer your question?
Yes.
Okay. All right. So Senate meetings turn into a soap opera. God bless. Why would you even want to get involved with that? Leave me out. All right. Question. What can you conclude about the relationship between three vectors if their box product would be equal to 0, which is totally a possibility? What does that mean about those three vectors? Any ideas?
They parallel to each other?
Parallel.
They're not parallel, but you're on the right track.
Orthogonal.
Nope.
No?
Can you imagine if you took your foot here and you stomped on this box? Boom. And when you stomped on it, let's say the W still pointing there, and then the U vector would kind of get squashed like here. Do you see that they'd all be flat on the ground? Does everybody see my picture? I stomped on the box and then I squashed everything and flattened out the box. Please say yes.
Yes. So they're all on the same
That's
plane.
RIP box. Do you see that these vectors are not parallel to each other at all? Parallel means, they're parallel. They're not intersecting. They definitely are all intersecting. So these puppies are definitely not parallel to each other. But there is a word that describes this flattened box, which has a volume of 0. These vectors are coplanar, which means they live in the same flat plane. So the vectors are coplanar, contained in the same plane. Write this down. Now, how would you, if somebody said, hey, here's three vectors, are they coplanar? Yes or no? So a different problem, but it's still using the concepts I've talked about in the last 15, 20 minutes. What would be a quick and dirty way for you analytically, not pictorially, not draw the picture and see if they're all living in the same plane? You don't have time for graphing stuff like that in 3D, trust me. How would you do it? You would show box product is equal to
0.
0. Exactly right. You just go, hey, and you do the 3x3 to determinant that I just did up there, or some of you did also, and you would show that this is true. And then you'd be done. You're like, hey, if I get a box product equal to 0, that box is flat. And that means those vectors are coplanar. They're all contained in the same plane. Cool. Now, here's a different question that has nothing to do with the box product and all of it. It has to do with what we've been talking about in the last week and a half. And this is a little bit tricky. I don't expect you to answer it, but if you do, God bless. How would you prove that 3 points, not vectors, are collinear? So points are not vectors. So like here's A, here's B, and here's C. These 3 points are not collinear just because they don't live or they're not contained in a single line. However, if C were moved over here and I can draw a straight line between A, B, and C, so they're all sitting on the same line, then they are indeed collinear. But how would I prove it using some of the interesting stuff that we've talked about this last week, even this week?
Use the properties of vectors and maybe make a system of vectors like A to B or B to C.
You're on the right track. Perfect. So if you formed the vector AB, and then you also formed the vector, say, BC, LO, perfect, that's a good thing. Then what?
Maybe you work with a scalar multiplier.
Yes, you would show that they're parallel to each other. Then show they're parallel. How would you do that? There's 2 ways to do it. And both ways are fine. And both ways you've learned with me already. Okay, let's go over way number 1. Way number 1 to show 2 vectors are parallel is show that one is a scalar multiple of the other. Like AB is equal to some scalar like 2 or -5 or what the hell times the other vector. That's one way. Or we learned this with cross product. Do you recall that if you take the cross product of 2 vectors and you get the 0 vector, that means that those 2 vectors are parallel. That's another cool, quickie way to show that 2 vectors are parallel. So either way, so basically what I'm saying here is I'll just say AB cross BC equals the 0 vector. Or you could do what I just wrote down there. AB and AC, Nick, can also be done. So, or, Nick, you could show AB cross AC equals 0. Same thing. Perfect. Either way. What does NSFW mean?
Not safe for work.
Oh,
It's okay, I'm too late. The apocalypse happened, and now the chat will be permanently disabled.
I don't know what to say. Maybe your internet froze. I'm going to skip problem 5. It's pretty fun, but it's pretty hard, and I'm kind of running short on time. But if you want to see me do it, come to office hours. It's pretty fun. By the way, the answer is theta equals 60 degrees, in case you care. Okay, so let's do torque and wrap up cross product so I can get into the next section. So, yeah, I love Dilbert. A few times a week I like to read Dilbert, and he usually has some funny stuff, so I just thought that was hilarious. So for you physics buffs, let's do another application of cross product, shall we? Torque. You've probably heard of torque. So it's an application of cross product. So check it out. It's pretty easy if you understand cross product. Here's the idea. Suppose you want to loosen a bolt with a wrench. And as you apply force to the end of the wrench in the plane that's perpendicular to the bolt, you get kind of a twisting power, that's called torque. So that's basically what torque is. It's like a twisting power. So my little picture here, I hope you could get behind, you know, you're trying to apply some sort of force. In this case, the force is a little bit off kilter here. But you have 3 things that you want to deal with. You've got the length of your wrench that come into the situation here. You have the magnitude of the force that you, the person, is applying to the edge of the wrench. And then theta is the angle that the force you're applying makes with the wrench, or makes with the R vector, if you will. So this is the angle that F makes with the wrench. Okay. Fine. Now, I can't spell. I am sorry. That looked terrible. Okay, so they use a tau, this is tau, for torque, and that's your twisting effect or twisting. It turns out it's the cross product of your wrench vector with your force vector. Okay, and you can think of your wrench starting at some O, so like over here could be your O, and ending at P over here, so the vector OP. So the torque vector has a magnitude of the magnitude of the wrench vector crossed with your force. And remember that these two things are equivalent. So there's two ways to get your torque depending on what kind of information they're giving you in the situation. So you're going to get like a word problem. Yeah, it's going to be on the quiz. Yeah, you need to know it. It's not hard. Do your homework. So let's just do a quickie problem that's going to be on the quiz. So let's say you've got two tightening a bolt situations, okay? Here's one where you have a 20 Newton force applied to a wrench and 60-degree angle with the wrench, okay? And the wrench is 0.15 meters long. So that's situation number one. The situation number two, you're applying a force of, I think it's still going to be 20 newtons here, but the angle you're going to make is different. So you got an angle of 135 degrees, and your wrench is a little bit longer, 0.25 meters. So which one is going to give you the most torque? So it turns out if you do this problem, so here we'll do torque 1 here. This is going to be sine theta times the length of the wrench times the magnitude of your force. So this is going to be sine 60 degrees multiplied with 0.15 meters multiplied by 20 newtons. And then I think this is square root of 3/2. Multiply it all out, and I get 2.6 Newton meters, or 2.6 joules with a J. Same. Over here in situation number 2, my torque, I'll call it torque 2, is sine of 135 degrees multiplied by the wrench length, which is 0.25 meters, and my force is still 20 newtons. Fine. And this is approximately 3.5 Newton meters, or 3.5 joules. So this guy is the winner. This one has more torque, probably helped by the length of the wrench. Okay, and then I have a meme for you. And we're officially done with cross product. Congratulations. So wrap that up.
I mean, I agree.
Yeah,
Yeah,
you agree?
Better than series.
yeah. That was seriously boring.
Sometimes I get people agreeing in the beginning of class, and then about 2/3 of the way through the semester, they're like, no, I think Calc 2 was easier. And it's like, okay, you're entitled to your opinion.
Professor, quick question.
Yeah.
So torque is basically the work formula, but with an angle of application added in, right?
It is like a work formula, yeah.
Okay.
Yeah, and you've got that angle in there because you're using projections essentially.
All right. So the more the angle is perpendicular to the surface of application, the more work is being done, right?
Mm-hmm.
Okay.
So when is your cosine maximized, actually? That's kind of what you want to do, look at. Right? So you're going to have more torque, when your sine is maximized. So sine gets maximized sine hits a high at 90 degrees. So that's the biggest it could get because it's a 1. Otherwise, it's a fraction of 1. Okay, so I hope that helped. If not, do some homework, come to office hours, all that good stuff. Okay, now we're going to hit lines and planes in space. Now let me say something about this lecture. Am I lagging for you guys? Rosie?
No.
Okay, it may be your internet, Rosie. I know you said you have pretty wonky internet, right?
Specifically,
Hello?
yeah. But
You got crappy internet.
it's just
Well, hey, Rosie, Rosie, I got a secret for you. Rosie, can you hear me? Rosie, can you hear me? My middle name is Messed Up Internet. I have lots of internet problems myself, so I can relate. It is really frustrating. Can you guys still hear me?
I hear you.
I can still hear
Yeah, I
you,
can hear
Professor
you.
Rasky.
Okay, I'm just checking, because my internet's wonky, man.
I can still hear you fine.
I'm spending $135 a month with Cox, and I still have crappy internet. I bought a new router, crappy internet still. I don't know what else to do. But and then other people are going, don't get AT&T because that's even worse than Cox. And I'm like, crap. Well, look, see that, Rosie? You got AT&T. That's your first mistake.
Or like you move closer to the router or even like plug it in. That's
Yeah.
most optimal.
I'm upstairs now because I found when I was doing all my Zooms downstairs in my kitchen, because our router's upstairs, it was a nightmare. So I've had to move upstairs. So that's
Yep.
helpful if you can do that for yourself, okay? So what is up with my PDF here? Oh, it's asking me something here, yes. Okay. So now we're going to do lines and planes in space. So what? This is going to seem like it's got nothing to do with nothing, but it's got everything to do with everything for the whole semester. So we're going to look at lines in 3D, and then this idea of a surface that's basically like a flat table, plane, but it goes off in all infinity directions. And so what we're going to try to do is we're going to try to get equations for a line in space. Yeah, there's more than one, that just for one line in 3D. And then we're going to get a single equation for a plane. And we're going to use a lot of dot product and cross product. And Elvis already got Ethernet cables up the wazooby, and it helps me not at all, okay? But thanks for the tip. Yeah, I think Jordan's got the right idea. I think if you surgically attach your router, Jordan, you're so funny. Did it work? I want to say that we're not going to get through all of this lecture. Look how long it is, people. Good God, man. See all these pages? So may I give you a friendly reminder? I said this the other day, but you probably forgot. In your modules, if we go back to your Canvas account, in this week's module, that's week 2, you're going to find the last part of this lecture, which we'll try to get through as much as we can up through Friday, but I'm thinking I might not make it. It's things to know, lines and planes and space extra. So there you go. All right. And look at all these videos I have posted for you. So in addition to rewatching my Zoom recording, if you still find yourself confused with this week's material, I encourage you to watch some of these other videos that are posted here. They're not me, but they're really good, and they're short too. Projections, cross product, and then lines in space, equations of planes. And we're going to do distance between a point and a plane and distance between a point and a line. So we're going to look at distances in 3D. So why do you care about all this crap? So here's a reason. Some of you are really into gaming, aren't you? I understand you guys are gamers. You know, maybe you're going to get into computer science because maybe you want to be a gamer and create gaming programming. Cool. Well, then you care about 3D, and that's why you're here. And you care about finding distances between lines in space and planes. But in order to figure out a line or, you know, straight lines in space or planes in space, you got to first be able to talk about those guys intelligently. Okay? So what is bottleneck of MBS? I don't know what that means.
If you have an external connection to your router, what happens is sometimes the connection will it is only rated for a certain megabytes per second of data transfer. And
Oh,
so
MBS,
basically,
megabytes per second. Okay, yeah, I have that one. Usually I see it as MBPS, megabytes per second, right? Don't you
Oh, right.
this, not MBS? That's just
Yeah, that's it.
the same. My megabytes per second in my husband's desktop, which is on the other side of this wall, since we upgraded the internet, he gets all the good stuff. For some reason, he gets 500 megabytes per second. In my room here, my stupid desktop might get 50. And then my
250 is pretty good though. What?
my Surface might get 30, 40, or 50. Yeah. I don't want to talk about it anymore. I just get really pissed off. I just want to reach through the phone line, grab Cox by the neck, and strangle them. That'd be a good thing. Okay, let's talk about lines in space. What do you guys know about lines in 2D? Let's do a review. This is algebra. So do you guys remember that in algebra, you know, here you go. You know, somebody goes, hey, kiddies, there's a point P, there's a point Q. Do you know how to find the equation of the line through point P and point Q? And you should answer, sure I do. And it would look, after you did some work, find the slope by doing, you know, difference of the y's over the x's and use the point slope form or the whatever equation of the line that you prefer, you would eventually get what? Y equals mx plus b? Please say yes.
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 Sure.
Yes.
We all know that. And if you don't, I can't review algebra 4A here in Calc 3. So hopefully you remember all that stuff. So here's the interesting thing. In 2D, you can represent one line with one equation. Okay, duh. Yeah, but that's not the case in 3D. Here's what's weird. In 3 dimensions, if you have a line, here's our line right here, we're calling it L. You actually need 3 separate equations to describe the one line. So when I give you one of these homework problems or quiz problems on Sunday, and I'm going to need 3 separate equations to describe a single line in space. That is whack. And that's what I'm trying to say here. And further, these 3 equations are referred to as parametric equations. And if you took Calculus 2, you're going to remember that in 3D, remember in Calc 2 the last week of class or so, you had parametric equations. Does anybody remember this? I'll open it up.
Yeah.
You probably forgot everything you learned, which is fine, but we're going to review it, but we're going to review it on steroids in the next 3 weeks, so pay attention. So in Calc 2, you did something called parametric equations, and that was like 2 equations where you had a third parameter, usually t, and then you use your graphing calculator in parametric mode, and you were able to graph curves in 2D. Fine. But we're still going to do 2D parametric, but we're also going to crank it up to 3D parametric. But again, if you don't really remember much, you better focus up the next 2-3 weeks because we're starting right here. When you get the parametric equations, see that here, parametric equations for a line in space, there's going to be 3 of them, all wrapped up in one little package. So you need to get that, okay? So let me derive it for you, and it's real quick and dirty derivation. So if you see this little diagram here, this will help you get the derivation, and knowing the derivation will help you not forget it. So hopefully you can tell that my line here has 2 points on it, P and Q. Yeah, so what? Well, there are 2 pieces of information you're going to need when you come up with these parametric equations for a line. You're going to need 1 point on the line, at least 1 point. Hey, here we've got 2. Woohoo! Okay, that's great. And then you need a direction vector. So the direction vector is a vector that's parallel to your line. It could even live on the line. I don't care. Either way. So this direction vector I have down here, I hope you can tell, is indeed parallel to my line. And so his little components, A, B, and C, are referred to as direction numbers. Okay, fine. So in English, what we're saying is this line here, L in space, consists of all the generic points Q that have an arbitrary X, Y, and Z coordinate. And what that means is you can slide Q over here, or if you want, you can move Q over here. We don't know what his coordinates might be. We'll just leave them as arbitrary X, Y, and Z variables. P is going to stay fixed because that's the point that we know lives on our line. So we're going to say the line L, is going to consist of all the points, all these infinity points, for which the vector PQ is parallel to V. And this is the important statement. So what do you guys know about parallel? So hopefully you remember that that means that PQ is a scalar multiple of V. That's what we learned last week. And then further, we can say PQ is equal to some scalar. And instead of C, I'm going to use T, because that's the tradition. T is going to be our parameter, TV. And then if I form the vector PQ by doing terminal minus initial, terminal minus initial, terminal minus initial, and that's going to equal T times V is going to look like TABC. So let's distribute the T over the brackets. So I'm going to have AT, BT, and CT. And now you're going to use equality of vectors. What does the equality of vectors idea tell us? If one vector on the left-hand side of an equation is equal to the vector on the right-hand side. Hello?
So you get three equations like x minus x1 equals at,
Yes.
y minus y1. Yeah.
Yeah, write that down. So what that means is x minus x1 had better equal at. The x components have to be a match. And then you have to equate the y components. So that means y minus y1 had better equal the bt. And finally, you've got the z components had better be set equal to each other. And now you're almost done here and we're ready to go to the theorem. For each of these equations, you're going to solve for x for the first one. For the second one, solve for y. And then the third one, you're going to solve for z. So you do that real quick, and you're going to get parametric equations. Okay, so the parametric equations are x will equal x1 plus some number a times t. Y will equal a y1 plus b times t, and z will equal z1 plus c times t. Those three equations wrapped up in a big old package describe a single line in space. Well, what line? It's a line L who is parallel to the vector v, who's got these little scalar components a, b, and c, and passing through the point P with coordinates x1, y1, and z1, and is represented by the parametric equations. Yeah, I know, it's a lot. You think your week is bad. You should feel sorry for my Calc 2 people. Did you know that on Monday we did hyperbolics? Today we're going to do area between curves, arc length, and surface area of revolution. And on Friday we're going to do differential equations and exponential growth and decay. And yeah, they're going to have a quiz on all of that. They're going to hate me.
Good times, Calc 2.
Good times, baby. And they're like you. You go too fast. We all as professors have to go fast if we're going to have to cover the things that we have to cover. I feel nothing for them. Is that right, Nick? You survived. Let God sort it out. Huh. Cruel and heartless you guys are. Don't you have any compassion at all?
We're in Calc 3. Like, all of it's been ringed out during Calc 2.
Okay. All right.
Yeah, we already suffered that part of our lives.
Okay, no more of that suffering. All right, now there's another thing called symmetric equations, which I'm not a fan, okay? Prof. Rasky, not a fan. But I do want to show it to you so you do have an idea. There's another way to represent a line in space. And here's how you get it. You eliminate the parameter t. So if you solve for t 3 times, so if you solve for t with the first equation, you would get the difference between the x's divided by a. And so that's basically t, but that t has to equal the t that you solve for with the second equation. And then if you solve for t a third time with the last equation, you get a third result. And this big compound equation all together is one big old package is called the symmetric equations for a single line. And I hate this way. You know why? Why is this inferior to why is this inferior to parametric equations? Anybody want to guess?
It just looks worse.
I'll give you a hint. What number that if you put it in a denominator would make it undefined?
0.
Yeah, so if any of the direction vectors components are 0, this symmetric version is crap. And that's not cool. That's why I never use it. I like this. This is me like right here. We like that. Okay, let's do a couple easy examples here, shall we, people? And then we'll wrap it up. And then next time we're going to do way more equations of lines and planes and get to the distance formulas and so on. Okay?
So
Do
can
your
the
homework. Here
can
we
the-
go. Now, I'm never going to give you something as easy as example 1 because it's way too easy, but I want to boost our self-esteem a little bit. So here we go. So we're going to find both the parametric, which is happy face, yay, and a symmetric, unhappy face, equations of a line L that pass through this point and is parallel to this vector. Okay, so folks, this is your point P. Remember I told you you need 2 pieces of info to get the equation of a line in space, a point and a direction vector. There you go. They handed both of those pieces of info on a silver platter. We don't even need to think. No brain cells. You just plug and chug. So you're going to use this formula, these formulas here, where the x1, y1, and z1 are the coordinates of your point, and then the coefficients for the parameter t stays a variable, that's your parameter, are simply the direction numbers. Here's your A, B, and C. This is your x1, y1, z1 when you plug into the formula. So if you look, I'll just copy down the formula. The formula looks like this for parametric. So we're just going to do what we need to do here. So we're going to have x is equal to what? The x coordinate of p plus 2 times t, at. Y is equal to the y coordinate of our point plus the y component times t. And the last parametric equation is 4 plus 3t. Boom, I'm done. There's the parametric equations. That represents a line in space. Now what about the symmetric, which I hate? Okay, well symmetric is, it's like a single big old equation where you have 3 things set equal to each other, 3 expressions, which, ugh. So for us, it would look like x minus 1 over a, but a is 2. That better equal y minus negative 2, but that's really y plus 2 over negative 4, and that's equal to z minus 4 over c, which is 3. And this version I don't like, but this is the symmetric equations. All right, you've seen it. There's an example. I'm going to do one more example and then we'll call it. But any questions on that one?
No.
I see you guys having fun in the chat box, which is, I'm okay with it, but I also want you to, you know, be able to handle this. You know, can you multitask? I don't know. They were saying it's not good for your brain to multitask. I know I do it all the time. I'll be in the middle of checking email and go, oh crap, I got to go do this, and then I'll forget what I was doing there, and it's a nightmare.
Yeah, it's inefficient according to
It
science.
is. And then I basically forget a whole bunch of stuff at the end of the day, and then I'm like screwed. Like I was supposed to be in a meeting yesterday at noon. I had it on my calendar. It was on my computer, and blew right by me. And like a half an hour after it was over, I went, I was supposed to be at a meeting. All right. So let's answer this question really quick. And you should know this, but it's kind of tricky, so I'm not expecting everybody in the room to get it. I claim that none of these answers we got in the previous problem are unique. Like I could have had different answers and they would have been legit. Why not?
I'm sorry, what was the question again?
Okay.
Why is it not legit?
Here's the question right here. I'll circle it here on the screen, right there. Neither parametric or symmetric equations for a line are unique. In other words, I could give different answers, and I can't just give any old answer, okay? It has to be specific, okay? But I have to be careful when I'm checking your paper, and so does my math lab. They have it set up where the algorithm can handle you giving different answers, but it's still being legit, and you'll still get the credit. Why?
Because you could have used another point on the line.
Yeah, you guys get that. Here's a picture of a line. Do you get that there's infinity points on the line, right? Because it goes on forever and ever in both directions. Well, they gave a point P like over here, you know, this specific point, 1, -2, 4. But do you get that I could have just as easily picked some other weird point over here, Q, with as long as it was on the line, and got some other values. So instead of having a 1 and a -2 and a 4 right there, I would have had whatever those other coordinates, as long as that point coordinates are something on the line. Is that clear? Would have been just as legit. Now, how can I get a different point on the line? I know that they gave me P. I'm like, hey guys, thanks. That's a cute little point on my beautiful line. How do I get a different one? What if somebody said, right now, I want you to give me another point on the line, quick? How would you do it? I'll give you a hint. Look at these equations. How would you get another point, X, Y, Z, on the line?
Would you multiply it by some arbitrary scalar?
No. You would simply pick a value for T other than 0, because if you plug in T equals 0, it'll give you the point P right back. Plug in, say, where the parameter T is equal to 1. And then you get an X coordinate of what? 3. Then -2 plus -4 would be -6. And then when I plug in T equals 1 for the Z equation, 4 plus 3 is 7. Boom. There's a point I claim that also lives on my line. Hello, if you're following along, you're doing great. And you probably understand the parametric equations that you learned in your Calc 2 class. If not, listen up, because we're basically reviewing. So the answer is, you know, letting T equals 1 gives an alternate point. And that's one way your line would have different equations. What's a different way that you could have something? Well, you know this direction vector they gave us? Remember, the direction vector just has to be some vector that's parallel to your line? Well, I could come up with a different vector that's parallel to V. How about the opposite of V? That would work, or maybe double V. That would still be parallel to your line. So these coefficients of your parameter T, as long as they're multiples of the direction vector, it's still legit. So any multiple of V, so this is an alternate way you could have different answers, any multiple of the direction vector V can be used as your direction vector, okay? So let's just do one more example, and then I'm going to be done with lines, and we'll start with planes next time. And rewatch this video I'm going to post tonight multiple times if you feel like you just got run over by a bus after today's lecture. Okay, suppose instead of giving you a point and a direction vector, no, that was too easy. I'm never going to give you something that easy. What if they just give you 2 points on the line? You know, say a P and a Q. There's a line, and they give you a P and a Q with the coordinates. Boom, you're done. You did this in 2D when you had an algebra class. When they gave you 2 points on a line in algebra, you were able to work it. You need to be able to work that same type of problem in analogous fashion here in Calc 3. So here we go. Good news, we do need a point on the line, and they gave me more than 1. They gave me 2. Fine. But we don't have a direction vector for the line because we need one. So how could we get one if we have 2 points that live on the line? I'm going to open it up.
Terminal minus initial.
Good. You just form the vector PQ. Very good. And that will serve as our direction vector for the line. Fantastic. So I'm going to do that now. Terminal minus initial, terminal minus initial, terminal minus initial. And I get 3, 2, 5. Yeah? And these are the A, B, C, my direction numbers for my line. So now if I look at the parametric equations general formula, I have my A, B, C. That's the direction numbers here. But who should I use for my point on the line? Should I use P or Q, or does it not matter?
Doesn't matter?
Doesn't matter, correct. That's why you and me might have different answers for this result here, because you might have decided, oh, I like P. And then I might have decided, well, I like Q better. Hey, you know, let's have an argument. And both are correct. They're both good. So how about if I, oops, I don't know what the heck I just did. I hate PDF annotate. So I need a package, so X, Y, Z here. And then how about if I use point P? So I'm going to have -2 plus 3t, and then 1 plus 2t. These coefficients on the t, I'm using my direction numbers over here. And then 0, and I don't need to even write the 0, 0 plus 5t. You don't need to write that. So here I use the point P. But what if I decide, oh, I like Q better? Fine. Then an alternate answer that's just as good would be, you would use the coordinates for Q. That's fine. I don't care. Pick your poison. They're both legal. And give an alternate answer. So I claim that both answers are fine. Any questions on this? Because I'm done with today's lecture. If you need to leave, bye. Otherwise, stick around and ask me some quick questions. And if you still want more questions, because I got another class here pretty soon, I got to teach in 10 minutes. Remember, I have office hours today, so I'll see you there also. I'd be happy
Professor,
to.
if you plugged in points